In this video, we're going to continue our discussion of section 3.7, improper integrals. In the last video, we talked about how to calculate or evaluate an integral where we had an infinite interval that we were integrating over. And that's the first type of improper integral. The second type is when we want to integrate a discontinuous integrand. So basically somewhere in the interval there's a discontinuity. The first two types, type 1 and type 2, deal with discontinuity at one end of the interval. So like in number 1 there's a discontinuity at the endpoint B, and in 2 there's a discontinuity at the starting point A. And usually what that means is there's some sort of asymptote. So usually it's a discontinuity from an asymptote, a vertical asymptote. So say we had the interval from A to B, but it was discontinuous at B, it would probably mean that the graph would look something like this. So you have, it starts at A, and then it ends at B, and then at B there's some sort of vertical asymptote, and so the graph might look something like this. And when we have that, we can't actually include B as our upper limit. We can't do that. So we, kind of like what we did in the last video, we're going to let the upper limit be T. And then since we're approaching B from the left, we're going to let T approach B from the left. And then 2 is similar, except in the second part here, the discontinuity is at the starting interval, the start of the interval. So again, probably a vertical asymptote there. And then part 3, we'll take a look at an example of 3. 3, we have some discontinuity in the middle of our interval from A to B. So without getting too much into the details there, I think it's better if we just look at an example. If we scroll down here to example 3, it says evaluate the integral from 1 to 2 of dx over 1 minus x. So if I go ahead and rewrite this integral here, we have the integral from 1 to 2 of, I'm going to rewrite it as 1 over 1 minus x and then put the dx on the end. And you can see that there's a problem here, because if I were to take 1 minus x and set it equal to 0, we can see that if x equals 1, that there's going to be, the denominator is going to blow up, right? We can't have division by 0. So what we're going to have here is a vertical asymptote at x equals 1. So let's go ahead and look at the graph of it though. So I already have it open here in Desmos. Here's the graph right here, and you can see I drew in that vertical asymptote. Remember, the interval goes from 1 to 2. So if our integral is going from 1 to 2, and we have this vertical asymptote on the left-hand side, we're going to have to approach 1 from the right. And so let's go back up to the definition at the top of the page. Which option are we dealing with here? Are we dealing with option 1 or option 2? And for example 3. Hopefully you picked option 2. That would be the correct choice. And so we want to, since the asymptote is on the left side, since the asymptote is at A, we want to let A be T, let that lower limit be T, and then we're going to take the limit as T approaches A from the right. Remember, we're approaching, the function is approaching 1 from the right, that vertical asymptote at 1. Okay, so let's go ahead and set this up. We can rewrite this integral as a limit as T approaches 1 from the right of the integral from T to 2. And then we have 1 over 1 minus x dx. Okay, so question. What method are we going to use to evaluate an integral that looks like this? What are your thoughts on that? Okay, so hopefully you want to do a u substitution, and we want to let u equal 1 minus x. which means du is equal to -1 dx, or negative dx, or dx equals negative du. And that means we're also going to need to change our limits for this problem. So let's go ahead and rewrite this. We have the limit as t approaches 1 from the right, and we have our integral. Instead of 1 over 1 minus x, we have 1 over u. And instead of dx, we have negative du. So I'm going to go ahead and write the du on the end and then scoot the negative to the front. And because of the negative, I'm going to put a bracket around this whole integral just so it doesn't look like it's the limit minus the integral. It's still the limit of all that. So we have the limit of that, and then we have to change our bounds. So lower bound, x is equal to t. So when we plug t into our u equals 1 minus x, it's no longer 1 minus x, but 1 minus t. So we have 1 minus t for our lower limit. And then our upper limit is now going to be what we get when we plug in x equals 2. So 1 minus 2 is negative 1. And we can go ahead and go a little bit further because now we can take the antiderivative. So we have the limit as t approaches 1 from the right, and we have negative. The antiderivative of 1 over u is the natural log of the absolute value of u. And we're going to evaluate this from 1 minus t, to negative 1. All right, then we can go ahead and plug our limits in. So we have the limit as t approaches 1 from the right, and we go ahead and plug in our upper limit, and we have the negative natural log of the absolute value of negative 1 minus the negative natural log of the absolute value of 1 minus t. And we know that the absolute value of negative 1 is positive 1, and the natural log of 1 is 0. So that's 0. So we can simplify this down a little bit more. This is equal to the limit as t approaches 1 from the right. Notice we have negative minus a negative, so that's going to be a positive natural log of 1 minus t. And we can't plug 1 in. We can't use direct substitution here because 1 minus 1 is 0, and we can't take the natural log of 0. So if we're approaching 1 from the right, that means t is just a little bit bigger than 1. It's a little bit bigger than 1. So if we take 1 minus a number that's just a little bit bigger, we're going to get a number that is really small. And the natural log of a really small, and that's actually a negative small number, right? But because of the absolute value, that's going to turn positive. So what we have, again, is the natural log of a really small number. The natural log of a really small number. And you can go ahead and confirm this in your calculator, but if you plug in like the natural log of 0.00001, it's a really big negative number. And this is, of course, can also be confirmed with a graph. If you graph natural log, remember there's a vertical asymptote at x equals 0. So as t gets really, really close to 0, as t gets really, really small, the graph goes down towards negative infinity. And so that's what this approaches. This limit approaches negative infinity. So, question, does this integral converge or does it diverge? And if you said diverge, you would be correct. This integral diverges because we get negative infinity. Okay, let's do one more example. The next one, this is the last example we're going to cover, is just going to be setup only. So example 4, it says evaluate the integral from 1 to 4 of dx over x minus 2 to the 2/3. And where are we going to have a vertical asymptote in this problem? What do you think? Hopefully you said x equals 2, because again, if you were to plug 2 in for x, then you get 2 minus 2, which is 0, and we can't have division by 0. So yes, again, we're going to have a vertical asymptote at x equals 2. And let's take a look at the graph of this. So if you look at the graph, you can see right smack dab in the middle of the graph at x equals 2, that blue vertical asymptote, x equals 2. And what was our limits for this problem? Our limits were from 1 to 4, so this creates a problem. Our limit goes from 1 to 4, and we have this vertical asymptote right in the middle. And if we're trying to add up all that area, it might mean that we can't actually add it up, because we just keep adding more and more area as we go into this peak of the vertical asymptote. And that was the problem we ran into on the last example. When we tried to add up all the area underneath the curve in example 3, when we tried to add up all that area from 1 to 2, we just added too much area below the curve. In other words, that red curve was not close enough to the asymptote, and so our answer did not converge. But we'll see if this one does converge. So again, our setup here, we're going to have to split this apart. So this is going to follow the third part of this definition on the previous page, where we have a discontinuity at some point C that's in the middle of our interval. So we have to split it up into two separate integrals. And so what that's going to look like is we're going to say that this is equal to the integral from 1 to 2, where that asymptote is, of 1 over x minus 2 to the 2/3, plus the integral from 2 to 4, 1 over x minus 2 raised to the 2/3. And because we have that vertical asymptote at 2, we need to create limit problems for each one of these. So take a second and on your own, pause the video and see if you can go ahead and write both of those limits by yourself. This is good practice. See if you can do that. Okay, so hopefully you were able to come up with the answer, this next step that you see here. Hopefully you're able to set up your limits the correct way. If you're still having trouble, make sure you contact me. We can go over it further. We're going to stop. I'm not going to go any further with this example, just to kind of keep the video from getting too long. But I would encourage you to go ahead and try to evaluate the rest of this one on your own to see if you can do that. I will post the solution, the full solution for example 4, so you can check your work. But after doing a few steps, it turns out that the answer for this is 3 times 1 plus the third root of 2. So in this case, does our area, does our integral, does it converge or diverge? And yes, the correct answer is that it does converge. So we can calculate the area from 1 to 4 underneath that curve. And that's going to go ahead and do it for this video. Thank you. Have a good day.